So welcome to today's lesson, which is on magnetism. So these are the learning objectives for today. Understand that magnets can repel or attract. Describe the properties of magnetically hard and soft materials. Understand what the term magnetic field line is. Understand that magnetism is induced in some materials when they're placed close to a magnetic field. And describe experiments to investigate magnetic field patterns. We'll actually do those in class. And describe how to use permanent magnets to produce a uniform magnetic field pattern. Quite a few learning objectives today. So, magnets and magnetic materials. So, basically, magnets attract other magnets. Okay, and magnetic materials that we know, at least in the elements, are the metals, iron, nickel, and cobalt, and also mixtures called alloys, which contain those three elements, are also magnetic. For example, steel, or stainless steel. So there's also hard and soft magnetic materials. Okay, so hard materials are basically permanently magnetic, like steel. Okay, so once they're magnetized, they stay as magnets. Whereas magnetically soft materials, for example, the metal ion, they lose their magnetism easily. Okay, and that's why they're used as electromagnets. And we'll look at electromagnets in more detail in other lessons. So, magnetic poles. So basically, there are two types of poles, okay? The magnetic poles are the areas of a magnet which exert the most magnetic force, and they're divided into two types. There's the North Pole and the South Pole. The reason why the North Pole is called the North Pole is it's attracted to the North Pole. There we go. So why are poles called North and South? So basically, if you suspend a bar magnet on a string, the north will begin to face the north. So that means that the North Pole is the north-seeking pole, okay, to shorten the North Pole. And consequently, the South Pole is the south-seeking pole. Okay, so the idea of a compass we see here as an image is an example of this concept. Essentially what happens is the compass and also the magnet, which is spinning on the piece of string, are being orientated inside the Earth's own magnetic field. And this is the laws of magnets. So like poles repel and unlike poles attract. So south and south poles repel, for example, and north poles repel. Whereas north and south poles, they attract. And that's known as the law of magnets. So in terms of magnetic field strengths, a magnetic field is basically the space in which a force from a magnet is exerted. Okay, it's where magnetic force exists. And all the magnets that we use, all these bar magnets, for example, and all magnets exert these magnetic force fields. Okay, that's why they can be detected. And you can use either iron filings or plotting compasses to determine where these electric field lines or electric fields are, okay, because they're all going to face in the same direction. As you can see that you can actually move the compass around and you can see where the compass magnetic field is moving. So this is an example of a magnetic field around a bar magnet. So we call the lines when we connect the dots, say when you're using a compass, the magnetic field lines. That's where the magnetic field strength is the strongest, okay? And the arrows show the direction of the force. So magnetic fields move from north to south. The stronger the magnetic field, the closer they are together. So you can see here on this image that at the north and south poles, the magnetic field lines are closest, and this means that the magnetic field strength is strongest at the poles. And you can see that also if you use iron filings again, you can see the magnetic field lines between two bar magnets. Okay, so between a north and south, you see that strength. And of course, as you can see, the lines are closer together in the middle, okay, which means the field strength is stronger. And you can see between north and south that there is that repulsion between the magnetic poles. So in order to produce a uniform magnetic field, so what is a uniform magnetic field? Basically, a uniform magnetic field is where the field strength is the same all the way throughout, okay, and it exerts a constant magnetic force around that area, or volume, actually. Such a field will actually consist, as you can see from the image, of parallel and equally spaced magnetic field lines. Okay? And this type of field is seen in the middle, right in the middle, when you put a north and south pole close together. So the important point too is the Earth is a giant magnetic field, okay, and it's a similar shape to a bar magnet, and it's basically thought to be caused by all these metals flowing inside the magnetic, the outer core, the molten outer core of the planet. And at present, the field line is like this, with the magnetic south pole situated in our geographic north pole. It's a bit confusing, but remember the north facing pole will face the geographic north, okay, so which means that it's being attracted to a south of a giant magnetic magnet, okay, which is the Earth, the south pole of the Earth's giant bar magnet, basically. Okay, and during the Earth's history, they actually do flip, okay, so at some point in the Earth's history and in the future, the magnetic north will become magnetic south and vice versa. Quite interesting. So, and finally, we'll look at induced magnetism. Okay, that's when magnetism is created in another a metal. Okay, so if you place a magnetic material, like iron, for example, next to a bar magnet, the material gets magnetized and it becomes magnetically hard. It will retain its magnetic field. Okay, so certain rocks like lodestone have been magnetized in this way and by the Earth's magnetic field. Okay, so that's the end of today's lesson. I hope you found it interesting, as I did.